Good evening. Dr. Eng here. Just wanted to go through this applied aerospace example. We've been doing a series of videos previously on the simple bending theory and the simple tolerance theory, and I've decided that I want to put more of a focus on applied examples and helping my viewers to be able to understand and why we calculate stress, why we calculate the Young modulus, how is the simple torsion theory applied to real life engineering examples. So I've got an example here where we've got a flat actuator, which is shown in figure 1. It's been modelled as a cylindrical bar and it's subjected to a compressive axle force of 8 kilonewtons, a bending moment of 55 newton meters, and a torque of 30 newton meters. It's being manufactured out of a 20 millimeter diameter solid bar and the grade 7075 T6 material aluminium alloy. So to be able to calculate the first part of this question is it's asking us at a point on the shaft surface determine the value of the compressive stress, bending stress and shear stress. So what we've done here is we've calculated the axial stress. So we know to calculate the axial load on the shaft, it is the load divided by the cross-sectional area. So to calculate the axial stress on the shaft, we've got a value of 8 kilonewtons, so 8 times 10 to the 3 divided by pi times 20 squared, which is the diameter of the solid bar, divided by 4. We would usually calculate the area of the cross section of the bar by with a formulation of pi d squared to the 4. That's where we've got that from. That then, and because the stress is compressive, so it would be a negative at the front. That then equals 25.48, and the units would be megapascals. Then, from the work that we've done on the simple bending theory, we get this useful explication where the bending stress is the moment divided by the inertia times y max. Y max can be calculated uh, usually by d divided by 2, which in this case would be 10. So we can see that the cross section of the shaft has been modelled here. It's got a diameter of 20 millimeters, and y max is essentially the distance halfway between. So to be able to calculate the bending stress, we've done 55 times 10 to the 3 divided by pi times 20 to the 4 divided by 64 times 20 over 2, which then has given us 70.02 megapascals. That's again the bending stress that we've just calculated. And the final part of the question is to be able to calculate the shear stress. So to be able to calculate the shear stress, it's tau divided by T over the torque divided by J polar moment of inertia times Y max. To calculate the polar moment of inertia, the formulation is pi d to the 4 over 32. In our case, it would be 20, which is the diameter of the solid bar, which would need to include in this formula, substitute into this formula. So the torque uh, uh, would be 30 times 10 to the 3. We've got J, which would be pi times 20 to the 4 over 32. And then Y max would be 20 divided by 2. You could really put 10 there, but I've just included that just for explanation. So once we put that into our calculator, that then gives us 19.09 megapascals. So the third part is where it's asking us to essentially model an element showing how the stresses would behave in this particular situation. So we've modeled the element. We can see the axial stresses and how the shear stresses behave in the directions. We've then added the bending stress and the axle load, which is acting in this direction. So the compressive load would be, axle load would be 25.48, and the bending stress would be plus 70.02, as we've calculated in the previous part of the question. We've then added those two together to give us 44.54 meganewton per meter squared. We've then had to calculate the principal stresses. So there would be two principal stresses acting on opposite sides. So the formula to calculate the principal stress would be stress in the x direction plus stress in the y direction divided by 2 plus half the square root of the stress in the x direction minus stress in the y direction squared plus 4 tau squared xy. We've got 44.54, which is a stress in the x direction, which we just calculated, plus 0 divided by 2 plus minus half. It's the square root of 44.54 minus 0 squared. So stress in the x would be 44.54. We haven't got stress in the y direction, which would be 0. And then plus 4, as in the formula, tau squared, which tau would be 4, which is the shear stress, times by 19.09. So, yeah. So 4, which is given in the formula, and then tau is what we've calculated, 19.09 squared. But remember, it's plus or minus, because so do put this into your calculator with a plus sign, and then just change that to a minus. That would then give you the two principal stresses. So we've got the first principal stress as 51.6 mega per newton meter squared, and the second principal stress that would be given is minus 7.06 mega per newton meter squared. Again, do not forget your units. It is an area where students do tend to forget, and they do end up losing 1 to 2 marks. So just keep that in mind whilst you're doing the question. So perfect. So if you do have any questions, please do leave them in the comment section. The plan is to continue to make more videos and create a channel where people are able to share their views, an engineering community, and we hope that you've enjoyed this video and that it's been useful. Please do remember to like, share and subscribe, and I'll see you for the next one. Thank you.